Hi everybody, we're back and we're starting part 2 of section 2. We've been talking about functions and now we're going to talk about the domain of a function. So the domain of a function is the set of all real numbers for which the expression is defined. So for example, if we had this function right here, f of x equals 1 over x squared minus 4. It's defined for all values of x except when x equals plus or minus 2. And you're thinking, well, how do you know that? And here's how we know that. We're looking at this function right here. We know that the variable is in the denominator. And what do we know about a denominator? We know that a denominator cannot equal 0. And we know that a denominator cannot equal 0 because of anything divided by 0 is undefined. So what would make x squared minus 4 equal to 0 to reach those undefined values? So we're going to go ahead and just solve this as if we were just solving for 0. X squared equals 4. We take the square root. Now remember, when you take the square root of something, you have to make sure it's plus or minus. And we get x equals plus or minus 2. But keep in mind, x equals plus or minus 2 is when it would be equal to 0. When it would be equal to 0. We don't want it to be equal to 0, and that's why it's not defined for x equals plus or minus 2. That's our exception for the domain. So what about f of x equals the root of x? Okay, well, we see this here. We see that x, always look for where the variable is. So x is in a root. And what do we know about a root? We know the values in it could be 0 or more, but it can't be negative. So if it can't be negative, that means that x can only be positive or 0, which is what this means. When x is greater than or equal to 0, that means positive or equal to 0. So we know it's defined only when x is greater than or equal to 0 only because it cannot be negative. All right, let's look at this parent function. So remember that parent functions are the simplest form of that type of function. And this is a root function, the parent form of the root of x. And this is what it looks like. It starts at 0, 0 because it can't be negative. Remember, we cannot go to the left of it. And it goes up and to the right. So let's talk about analyzing where the domain is. So let's talk about this. So as x, so remember the domain are only the x values of what's going on. So if our domain is only going to the right, so think about it this way. Our x values can only go to the right as we follow that function. So our x values are only going to the right. So we say that the x is greater than or equal to 0. For the range, remember that those values are our y values. And so for the range, we can only follow those values up because we also know that as we follow this curve here, the y values are also only going upwards. So we say that the range, or the y values, are that the y is also greater to or equal to 0. Greater than or equal to 0. Okay, so what's the y-intercept? So the y-intercept, or the x and the x-intercept, is at 0, 0. That's where our intercept is. And when we're talking about increasing on, okay, so that means they're talking about on an interval. So basically what they're asking are what values of x is the function increasing. Remember that the function The function values are really the y values. But we want to talk about it in terms of x. So what we're saying is, what values of x on the x-axis do we see that the y values are increasing? Well, I see the y values increasing really the whole time here. So for this case, it's increasing on the same as its domain. So we say it's increasing on parentheses 0, comma, infinity. And we use a parentheses when they're an kind of like a starting value, okay? Something isn't ever increasing on 0 because we know the value at 0 is 0. So we're not going to say it's increasing on 0. We're going to say that it's increasing starting at 0, going to infinity. The other thing I want to tell you about, remind you of, is our interval notation. So the way that we would say x is greater than 0 in interval notation is we start at 0 and we put a bracket there because it's equal to 0 as well. And then we say comma to infinity. Now we can't ever reach infinity, so we put a parentheses there because we can't ever really reach it. And the same thing goes for this. If y is greater than or equal to 0, we start at bracket 0 and it goes to positive infinity because it'll never actually reach infinity. Okay, so if we're talking about domains of the function, we are going to look at this one. Now this function is basically a relation of a set of points. We know that it's a set because of these cute little bracket things here. And the set is 1, 2, 3, 4, 5 different points. So we know that the domain, remember those are our x values. So for the domain, here we go, we are going to basically list our set of the x's. So we say the domain equals the set of, and we're basically picking the x values here. So we list them off, -3, comma, -1, 0, 2, 4. Now, if any of those numbers were repeating, we wouldn't list it more than once. But in a domain, we're not going to have repeating numbers if it's a function. Okay. What about this set? G of x equals -3x squared plus 4x plus 5. So G of x here is a function, and we want to know what the domain is. So basically, another way to think of the domain is when we're looking for the domain, we're looking for what are or what can the values of x be. Now we're looking at this. I can definitely put in 0. I can put in all positive numbers of x. I can also put in any negative values of x. So I don't really have anything that's restricting me at all. So what can the values of x be? And we are going to say that the domain is the set of x such that x is all reals. Okay, that's in set notation. In interval notation, we would say it goes from -infinity to positive infinity, goes on forever, and because infinities can't ever really be touched, that's why we use our parentheses around them. Okay. And our last one, we're looking at what's the domain of h of x equals 1 over x plus 5. So remember, what can the values of x be? Well, I do know that here, because our variable is in the denominator, there is at least one value that it can't be, because remember, a denominator cannot equal 0. So what would make x plus 5 equal to 0? Basically is what we have to ask ourselves, because we don't want it to be 0. So we're going to solve, and we get x equals -5. That would be the only problem. So we say, okay, that the set of this is that it's going to be all reals, but x cannot equal -5. Or we can say in set notation, the set of x such that x does not equal -5. Or in interval notation, we would say, okay, going from -infinity up to 5, up to -5, we would have to stop. Okay, we can't touch -5, so we close it with a parentheses because we're not touching -5, and then we join it with a union of from -5 to infinity. So these are the 3 ways we can list our domain. Listing it just in words, listing it in words, listing it in set notation, and then this is interval notation. Okay. Let's find the domain of this. Find the domain of the volume of this. So again, is there any restriction on what I can put in here? Well, because this is a cubed function, we know that anything that's negative that is cubed stays negative, and we can't have a volume that's negative. The same thing of, we can't have a sphere if the radius was 0 because it wouldn't be a sphere. So then we know that the radius has to be greater than 0, meaning it can't be negative and it can't be 0. Okay, so we know it has to be greater than 0. So our set notation would say that r is such that r is greater than 0. Or we could use interval notation where we say starting at 0 and going on to infinity. Okay, for this one, what's our restriction here? What can x not be? Now remember that a root can equal 0 or be greater than 0, but a root can not be a negative number. So let's figure out what would be in here to make it a negative number. So we're going to set 4 minus 3x equal to 0. We're going to solve. And we get x equals 4/3. Basically, this is the value that would make this not work. So we say, okay, the set of x such that x can be anything, but x cannot be, actually, it can, let's do this. It has to be greater than. It has to be greater than or equal to 4/3, right? Because if the value of x was 4/3, we said it could equal 0, which it can, but we just don't want it to be negative. So it has to be greater than or equal to 4/3, or we use our interval notation where we say we're starting at 4/3. Remember that bracket means we can touch 4/3. It can actually be 4/3, and then it can go up to infinity. And then this is how to use your graphing calculator to find the domain and range. So let's say they wanted you to find the domain and range of the root of 9 minus x squared, and you weren't sure how to do that on your graphing calculator. So basically, first you're going to start off with turning it on. If you don't know how to turn it on, it's right here. And then you're going to go to the y equals key. When you have your y equals key, you're going to type in your function and be careful of the parentheses. So for this function, because it's the root of 9x minus x squared, we're going to start off with the root. So you're going to have to go second root, and then you would type in 9 minus, and now your variable key is right here. This is x, and then you'll hit the squared key to square it. And then you'll hit your end parentheses. We have to be really careful about your parentheses. Once you've got that in for your y values, then you're going to go to graph. So anything that you go to graph, which is this key right here, always links back to your y equals key. So you're going to hit graph, and then you're going to get to see your graph fleshed out, and then you can hit the trace button and then toggle left and right to see what those values of x are and see those values. In this case, this root of 9 minus x squared is going to give us this shape right here, and I'll try to see if I can just draw it for you on here. So it's basically going to give us this. So this would be the graph that we would see on your calculator, and we would see something like this, okay? Kind of gives us this interesting half circle. And so when you toggle these values, you would see that from here, it starts at -3, 0, it goes up to 3, and goes down to +3. So we would say, okay, the domain is going to be the set of, basically we can say the set of -3 is less than or equal to x, which is less than or equal to 3. In interval notation, we would say from -3 to 3. And the range, kind of similarly, would be the set of y's from, now remember the range is really, this is our y values, and it doesn't go lower than the x-axis. So it stops at 0 and it goes as high as 3. Okay? So when it does that, we say it goes from 0 to 3. That's in set notation. And for interval notation, it starts at 0 and ends at 3. Interval notation is always a little bit more straightforward, easier, quicker to do. All right, last example. The path of a baseball is what we're going to be talking about today. And a baseball is hit at a point 3 feet above the ground at a velocity of 100 feet per second at an angle of 45 degrees, and it's given by this function is its path. Okay? F of x is the height vertical, which is the vertical part, and x is the distance from home plate in feet horizontally. Will the baseball clear a 10-foot fence located 300 feet from the plate? So basically what they're asking is, when the x is 300 feet, will the y be greater than 10 feet? Meaning, is it tall enough to clear the fence? So we can solve this two ways. We can solve it algebraically, where we say, okay, well, if I want to know when x is 300, we can go f of 300 and evaluate it. So we get -0.0032 x squared, excuse me, not x squared. We have to plug in the value, which is 300 squared plus 300 plus 3. And if we work all that out, we get a value of 15. So what they're saying is, okay, at the value of x equals 300, the y value is 15. What does that mean? Well, when the ball is 300 feet away from home plate, it'll be 15 feet tall or high. Well, in that case, we know if it's 15 feet high, looking back here, it's definitely tall enough to clear the fence. The other way you could have done it is graphically on your graphing calculator, that you would go back to this and plug this into your calculator. And you could either trace it over to x equals 300, or you could do something called a table. So after you graph your function in your y equals, you're going to hit graph, okay? That will show you a shape that should look like this. And then you can hit second graph, and you would see basically a chart of values, and you could either follow it down to x equals 300, or let me show you how to do this. To tell your values what you want them to do, you would go second and window, which would give you a table set, and you can set it where x equals 300, and then hit enter, and then it will give you a table where it shows you the value at x equals 300. So then when x is 300, basically you would see 300 where y is 15. And again, that tells you when x is 300 feet away from the base, the home plate, that the y is 15 feet in the air. So yes, the ball will clear the fence. And that's it for today.